Okay. So we are now in the recording mode. Okay. Okay, so maybe I'll start by trying to share my slides and start talking. So I'll so can you see the slides?
Yes.
Okay. So let me start with this. So my name is Tomasz Bulik. I work at the University of Warsaw and also at Astrocent in Copernicus Astronomical Center in Warsaw. And the title of this talk is Introduction to Geophysics. It's kind of funny. I am not an expert in geophysics. My field of expertise has been theoretical astrophysics, and I have been playing with some issues related to geophysics for the past several years because of my involvement in gravitational wave astronomy and gravitational wave physics. And as you will see later in this lecture, the gravitational, the geophysics or seismic physics, well, a part of geophysics is seismic physics, is closely related to gravitational waves, and this is the subject of this school. But also, you know, I mean, gravitational waves, also machine learning, but also geophysics. So, you know, I have been learning in this field for the past several years, and I'm enjoying and starting my adventure with geophysics. So I feel like not like an expert, but like I could say advanced student. So okay, how do I change slides here? Maybe I should view. So okay, so what is geophysics? So before starting to prepare this lecture, I was thinking, you know, what am I supposed to talk about, and what will this lecture be about? So geophysics is in general the science about Earth and the properties of the Earth. The really important part of this is the science of vibrations, so the mechanical structure of Earth, but geophysics is not only this, it's much more. So it relates to the Earth's shape, to its gravitational and magnetic fields, the internal structure and composition, dynamics, the motion of plasma, magma, and matter within the Earth, the physics of the surface of the Earth, which is plate tectonics, volcanism, rock formation, also the ocean physics, moving the bodies of water on the surface, including snow and ice, fluid dynamics of the oceans. It also includes the atmosphere and also the magnetosphere, which is the surrounding of the Earth, and electricity and magnetism in ionosphere and in atmosphere, also within the Earth, also the generation of energy in the Earth, and geophysics is now extended to include similar problems or similar issues that are associated with other planets that we start to understand, because we are starting to um, explore in more detail the planets in our solar system, and also now we also have some information about extrasolar planets. So it's a very wide field of physics, and it involves many branches of physics and many problems, and that are interconnected. So you could say that geophysics could be considered a part of astrophysics related to the physics of planets, with the special, of course, interest on the planet that we best know, that is the Earth. So the properties of the Earth that I will talk about are the following. I will talk a little bit about gravity, heat flow, seismic waves, magnetism, electromagnetic waves that are generated in the vicinity of the Earth, radioactivity as it relates to the Earth's properties, which is related to fluid dynamics, and also the properties of materials that the Earth is built of. So if you look at this is a range of issues that is very wide, and includes basically most branches of physics in your undergraduate or even graduate curriculum. So we all know, let's go now to gravity. We all know that the gravity on Earth, I mean the gravitational acceleration is about 9.81 meters per second square. And this is a value we learn at school, but if you look closely, this is only the average value. And the gravity, the mean gravity on the equator is lower than it is on the poles. And there are two reasons for this. One is that the Earth is not a perfect sphere, it's a geoid, and its radius on the equator is larger than the radius on the poles. Additionally, there is an effect due to the rotation of the Earth. So there's which adds to the acceleration, and the Earth is not uniform. So there are regions on Earth where the specific gravity is slightly lower and slightly higher than the average value. And you can see it on this graph where you see the map of the Earth with the gravity anomalies, and you see that these anomalies somehow in some places are related to, as you will see, seismic activity on the Earth, and to differences in the mean density in the regions underneath the surface of the Earth at various places around the planet. And this can be measured with precise gravitometers, and that tells us more about the structure of the outer part of the core of the planet. So the lesson here is that the planet is not as uniform as it might seem. The second issue that I want to talk about is the Earth's magnetism. So basically we are always told that the Earth's magnetic field is a dipole in the first approximation. And in the first approximation, it is a dipole, but if you look at the maps of the mean intensity or inclination of the field, you see immediately that there are lots and lots of deviations from the dipole structure. So the magnetic poles are off of the rotational axis, which is not unusual. We know many objects in the in the universe where the magnetic pole is not aligned with the rotational axis, and there is no particular reason why these two axes should be aligned. So there is a north magnetic pole in northern Canada, the south magnetic pole a little bit off Antarctica, south of Australia. But then the structure of the magnetic field, as you see, is a little bit more complicated. There is this region on the South Atlantic, which is called the South Atlantic anomaly, which is kind of, and this is a region of much lower magnetic field than anywhere else. And it has several consequences for astrophysics. One is that if you have satellites that move on the Earth around orbits, they are usually shielded by the magnetic field from the incoming cosmic rays. However, this shielding is much weaker when they pass over the Southern Atlantic and the center of South America. And this is a problem because cosmic rays tend to destroy CCDs or electronics and interfere with some measurements taken by astrophysical satellites, astronomical satellites. So quite often X-ray satellites are turned off when they pass through this region. Another consequence of the low value of the magnetic fields here is that that South America is a particularly good location for Cherenkov telescopes. So Cherenkov telescopes are the telescopes that look at Cherenkov light from incoming photons with the energies of TeVs, and the shapes on the Earth of the showers are affected by the strength of the magnetic field. So when the local magnetic field is low, these are particularly good locations for construction of the Cherenkov telescope arrays, and that's one of, but not the only, reasons why the site of the CTA, the Cherenkov telescope array, the next generation Cherenkov telescope, has been chosen to be in South America, in northern part of Chile around Paraná. Another reason is, of course, good weather, but that's another part of geophysics, which I'm not going to cover today. So we see the magnetic field, and the other point I want to make is that the magnetic field is not something that is static. It is generated by matter flows inside the Earth, and these matter flows inside the Earth are unstable. So here you see the moving map of the structure of magnetic field over the past several centuries. And that is possible because of the magnetic field has been used for navigation. And so sailors or generally sea traffic was measuring magnetic field over the past 5 centuries. To use it to know the true location of the North, and they always had to correct for the structure of the magnetic field. So you see that the magnetic field on the Earth, I'll let it go again. Okay, let me go up one slide. Okay, why has it stopped? Oops, it's something froze here. Anyway, you see that the structure of magnetic field is evolving on a time scale of 50 to 100 years, and this is an evidence of the changes in the center of the Earth. One particular thing about this is that there is always a discussion about the flipping of the magnetic poles, and we know that such flipping of magnetic poles north to south, exchanging their locations with a period of disappearance of the Earth's magnetic field have been happening in the past. We don't know what would be the possible time scale for such disappearance. We know that such periods have appeared, but when we are looking at geological sediments and the iron layers in rocks, but we don't know whether this period is 10 years, 100 years, 1,000 years. And this particular time scale is kind of important for humanity because life without the magnetic field would be very different. So, if we are looking at possible disasters on Earth, that's one possible disaster that may happen. But currently, we have, I think, other problems on our head. In the next slide, I'm showing the axial dipole strength in microtesla of the magnetic field. So you see that the magnetic field has not been constant. You have seen that its structure has been evolving, and it's not exactly dipole anyway. Now you see that the dipole part of the magnetic field has also been evolving, and it's been going up and down on the time scale of hundreds of years. Now it's going down. There are speculations that we are going towards a flip of the magnetic field. So if it continues like that, this flip should happen in a few thousand years. So we are still probably fine, but to be seen what will happen in the next 1,000, 2,000, 3,000 years, apart from other problems we might have here. Okay, so this is about the gravity and the magnetism. Let me turn now to electromagnetic waves. So we know that electromagnetic waves are generated in the Earth's atmosphere, and there are some varieties of the electromagnetic waves. Some are generated by lightning, some are generated by high energy electrons in the magnetosphere. So you know about the aurora phenomenon, which is generation of light by and not only light, electromagnetic waves at other wavelengths as well, by synchrotron emission in the magnetosphere. We also know that there must be waves in the Earth's core. I'm going to concentrate a little bit more here about the lightning and lightning strikes here. Typically lightning phenomena are happening at the rate of about several tens to 100 per second around the Earth. So there is lots of lightning going all of the time, and so there is lots of thunderstorms, mostly in the tropical belt, and each of them is generating some waves in the Earth's surrounding. So one particular type of these waves is as follows. So if you imagine the Earth's surface is conducting, and then above the Earth we have the ionosphere, which is also like a conducting sphere. So electromagnetic waves of sufficiently low frequencies are trapped in a resonant box that is a thin layer between the Earth's surface and the ionosphere. And if you have a closed box where you try to invoke electromagnetic waves, you will get resonances. There are several resonant frequencies that depend on the size and the shape of such a box. It's similar to resonances that you talk about if you try to confine waves, be it electromagnetic waves in a box or mechanical in a box, or mechanical waves, for example, on a string that is connected to a wall, right? So these waves that are generated in the Earth form resonances, and these are called Schumann resonances. And you can estimate more or less the fundamental frequency of some of waves that appear in this by knowing that the size of this sphere where we confine the waves is about 40,000 kilometers, given the speed of the electromagnetic waves, the speed of light, 300,000 kilometers per second, you expect the first resonant frequency to be somewhere below 10 hertz. And the Schumann resonances that are presented here appear at these frequencies, but these resonances are not very sharp. They are wide, so the first fundamental is 7.8 hertz, then we have 14.1 hertz, then the third order is 20 hertz. And the important part from the point of view of gravitational wave detection is that first of all, these frequencies are in the low frequency band of gravitational wave interferometers. We are currently approaching these frequencies, so typically we analyze data from 20 hertz or so and higher. Below that we have many sources of noise, but the interesting thing is that these are global resonances. So if you have gravitational wave interferometers at a few places on the Earth, they will be affected by the Schumann resonances at the same time. So you can expect that you will have collective or combined simultaneous effects due to Schumann resonances and electromagnetic waves in these detectors, and that can affect their sensitivity when you look for coincidences between the detectors in the low frequency band. So one thing is to look for, the way to prevent this is that you have to have precise magnetometers at each of the gravitational wave detector location. But it's also good to have a network of magnetometers around the Earth to be able to discover and detect all the the strongest bursts in these waves around the Earth. The other thing is that, as I said, there is about 100 lightning strikes around the Earth all the time. So these resonances, albeit much with lower amplitude, are excited all the time. So if you're looking at the long-term behavior and the long-term correlations between detectors, which people do when they look for the background of gravitational waves, this is a potential noise and potential hindrance, especially at these low frequencies. But this can be mitigated by looking at by measuring the magnetic fields and magnetic field variations around the Earth to screen and to be able to correct for the Schumann resonances, which obviously pass to the gravitational wave channel by coupling to all the metal parts in the detectors. Okay, the next part of the geophysics, Earth physics, is the energetics of Earth, or radioactivity and heat flow. So there is plenty of radioactive decays in the Earth, and this is powering the magnetic fields, plate tectonics, earthquakes, and geothermal energy. So the energy, Earth is not a dormant, cold planet. There is still some energy generation from radioactive decays of various elements listed here, like potassium-40, uranium, thorium-232, with very long decay timescales. And this causes heat flow from the center part of the Earth to the outer parts of the Earth, which in turn powers several known phenomena like plate tectonics, earthquakes, geothermal energy. The power due to the radioactive decays in the Earth is about 4 times 10 to 13 watts, which is about 4.2 times 10 to the 20 ergs per second. And me being an astronomer, I really like this CGS units like ergs per second. You can compare it to the amount of the energy that we are getting from the sun, and knowing that the sun luminosity is 2 times 10 to 33 ergs per second, knowing the distance from the sun and the radius of the Earth, it's easy to calculate that the power we are getting from the sun is about 10 to 23 ergs per second, which is about 1,000 times more. So you may say, well, you know, the energy coming from the center of the Earth is basically nothing. It's not going to affect the energy budget of the Earth, because it's just 0.1% of the energy budget. But that's not true, because the energy, most of the energy we are getting from the sun is immediately reflected, and it's radiated out. So first of all, you know, most of the part of the energy can be reflected by oceans and clouds, and then it's lost. Then the other part of the energy is heating the Earth, and it's coming in the as photons with the typical temperature or energy corresponding to the temperature of the sun, which is about 5,000 to 6,000 Kelvin. And then it hits the Earth. You know, the surface of the Earth has the temperature of about 300 Kelvin, roughly, depending on the location. So then it is emitted out at low energies, and the fact that it's emitted out in these lower energies as compared to the energy that it's coming in is the reason for the greenhouse effect, because the atmosphere is not as transparent to lower energy photons as it is to higher energy photons. So we have the greenhouse effect because of that. Anyway, this affects the atmosphere and the surface, really thin surface layer of the Earth. If you look at the deeper part of the Earth, if you look even at 100 or 500 meters below the surface, the energy from the sun has no influence whatsoever. So this power from the sun is affecting only the surface layers of the Earth and has little to do with the internal energy budget and internal working of the Earth. Over there, the heat flow is dominated by the radioactivity energy that comes from decays of these elements inside the Earth. Okay, so let me go now to mineral physics and to the properties of the material that the Earth is made of. So the mean density of the Earth is about 5 grams per cubic centimeter, but the Earth is, at least the Earth's surface, and as you can see, if you travel a little bit, is very diverse. There are regions and areas that are made of various types of materials. There is all science of geology that tells us about the properties of these materials with different compressibility, different electric conductivity, heat conductivity, and of course, different chemical composition. And this mineral physics is affecting the top layer of the Earth. If you look deep down, the composition of the Earth is much more uniform, and over there, this picture is becoming a little bit simpler than on the surface of the Earth. To realize what is the variation of, or the variety of the properties of different materials, I provide a little bit of an overview of different several properties of several materials. So you see that the range of properties is very wide. So apart from air and ice, the densities here the materials are arranged with the increasing density. So the densities are higher and higher. There can be from about the water density to several grams per cubic centimeters or megagrams per meter cube. The electrical properties or electromagnetic properties vary widely. The resistivity to electricity is can be in a very wide range, which is good because that provides us materials for for production of various elements and various electric materials that we can use, and thanks to which we can have this teleconference. The heat conductivity is also very wide. So this is a very rich physics. Now, if we go to the center of the Earth, we have this, apart from the, well, if we look through the depth, the mean depth on the surface of the Earth is a few grams per cubic centimeter. Then we have the mantle where the density grows to about 5 grams per cubic centimeter, a sharp increase in density to about 10 grams per cubic centimeters where we go to outer core, and then in the inner core, the density reaches about 12 grams per cubic centimeter. In a way, it's astonishing that the variation of the density over this radius of 6,000 kilometers is very small. You know, you increase the density by a factor of 3 to 4 over the entire structure of the Earth. To a good approximation, the zeroth approximation from the astrophysical point of view, the Earth can be considered as a uniform density sphere. And in the first approximation, we have to take into account that there are these layers that we see in the Earth. I'll talk a little bit more in a moment about the top graph, which is the seismic wave velocity, because there are this S and P types of waves. I'll talk about them in a moment when I talk about the seismic waves. The main point is that the velocity of waves is of the order of a few to 10 kilometers per second. So it takes about 20 minutes for a fast wave to cross the Earth, and a little bit more if the wave travels not across the Earth, but if it travels in the mantle and scatters of the core towards the surface. So then a seismic wave may take up to an hour to travel across the Earth. And for strong earthquakes, we see that. So, you know, if we have a strong earthquake somewhere in the middle of the Pacific, it takes about an hour, 50 minutes for this earthquake to be detected here in Europe. Okay, so let me go to the seismic measurements, and then I'll talk about the seismic waves. So we do seismic measurements with seismometers, and the seismometers typically measure the velocity as a function of time. So we attach it to the ground, and we try to measure velocities in 3 directions with different techniques. One of the easiest techniques to measure this is by the devices called geophones. A geophone is simply a magnetic coil on a spring, a magnet on a spring that is surrounded by a coil. And if we have some trembling of the ground, this trembling is passed mechanically to the geophone. The magnet on a string starts to vibrate and generates currents in the coil. These currents can be measured, and they are so such measurements are, of course, limited by the resonant frequency of such a device, but there are ways to extend their sensitivity with feedback loops, and that can lead to devices that can measure the seismic waves with the periods that extend all the way to about 100 or a few hundred seconds, and go down to frequencies of up to 50 to 100 hertz. So this is the range of frequencies that we are interested in mostly interested in seismic measurements, say from about a millihertz to about 100 hertz. And if you look at the measurements, sometimes we present the seismic measurements in terms of displacement or acceleration. But if you have velocity, if you measure velocity, you can also, knowing the frequency, you can translate it to displacement or acceleration by multiplying or dividing it by omega. The sensitivity of these instruments has to vary over a wide range of values. It goes from well, for the strongest earthquakes, we get acceleration of the order of close to 1 g, or velocities of meters per second. And when we look at the lowest sensitivities that we have to measure, this means measuring the seismic noise underground at very quiet locations. This measurements, the sensitivity, for example, at 1 hertz, has to be as low as 10 to minus 9 meters per second, or even lower, 10 to minus 10 meters per second, which is about 1 angstrom per second. So, you know, about the size of an atom per second. And there are instruments that can measure velocities as low like that. And for the gravitational wave experiments, these velocities are very, very high. So the gravitational wave experiments have to mitigate the effects of even such small vibrations as 10 to minus 10 or 10 to minus 9 meters per second. All right. So that has been a long introduction to various aspects of geophysics, and now I have a part that is related to what seismic waves are and how we find out about the seismic waves. So in the beginning, I was hoping to be able to do it using a blackboard. As we are having a remote lecture, this is going to be several slides that are filled with formulae. So I'll try to explain them in an easy way. You can follow them later and try to derive them, and I'll give you some references where more of this work in much more detail is being done. So what I'm going to do now is something that is a little bit contrary to my rules, because I don't like slides with many formulae, but here we are stuck with what we have. Okay, so let us imagine a little cube of material in a solid, and so the size of the cube is dx1, dx2, dx3, and there is several forces that are applied to each wall of this cube. Some forces can be perpendicular, but they don't have to be perpendicular to the cube walls. So these forces form a stress tensor Tij, and we have the coordinates or displacement Ui defined here. So the net force on this volume element dx1, dx2, dx3 is the gradient of the stress tensor. We have because we have to subtract the forces on that act on this volume element on two sides. So if we go to the with the limit of a small volume element, that translates to subtracting, which is differentiating. So the force on the volume Fi is di Tij, where di represents a derivative, and then dx1, dx2, dx3 to integrate over this, this volume element. Now, the mass in the volume element is rho times its volume, so this is easy. So we can now write the Newton equation of motion of such a volume element. So the mass times the acceleration, the second derivative of displacement, is the stress force, which is dj Tij. And then there are the external forces, the body forces. This can be the gravity force or some other force that is applied to the system. In most cases, we can assume that these external forces do not play much role. So we'll ignore this body or external forces and we'll concentrate on just the stress forces. Now, in order to find a wave equation based on this equation of motion, we would like to be able to express the stress tensor in the form as a function of the displacement, which we have on the left-hand side. And if we do that, we may get some form of equation where there will be a second derivative of with respect to time on one hand side and some derivatives with respect to displacement with respect to position on the right hand side, and that can be interpreted or solved as a wave equation. So at this point, let me ask if you want to have a break in this lecture, or do we continue without break?
I guess we can have a 5-minute break. So we continue at 10:05. How does that sound?
That's okay. Yeah, that's fine.
Okay, so we'll pause for 5 minutes, and we'll resume in 10:05. Okay.
So everybody get coffee, tea.
There is a couple of questions here.
Okay.
Chat. Maybe.
Okay. Well, when I share, I don't see the chat. Maybe okay. Let me stop the share.
Yeah.
Okay, I have some questions. I'll try to answer. Okay, first, Rob, well, I think I haven't seen these questions and they are kind of old. What is the amplitude of these modes? That's from Rob. This was about which modes? Was it about the magnetic modes?
Yes, that's correct. Yes.
Yeah, so these modes are the Schumann resonances. Have low amplitudes. I think that they are in tenths of micro Tesla. So, I mean, they are of the order of 10 to minus 6, 10 to minus of the Earth magnetic field, as far as I remember. And in order to detect them, you have to find electromagnetically quiet locations on Earth. So, for example, most of the Earth has lots of electromagnetic pollution, basically from all the electronics that we use, and also from power lines. You have to find the quiet locations. But the point is that with gravitational wave detectors, they are shielded from everything, and they measure things that are very low amplitude. And then we, okay, and they affect the measurement. The second question is, do these Schumann resonances disappear when going underground? Yes, but the long wave gravitation magnetic fields propagate a few kilometers into the Earth. So if we want to get rid of them, we would have to build gravitational wave detectors a few kilometers underground, which is completely science fiction. So they do disappear, but we will not be able to get rid of them by going sufficiently low underground. Okay, I see an amplitude of picotesla. So yes, I if that's Wikipedia, I agree with this. Yeah, so the magnetic component is dumped quickly, but electric is dumped quickly, magnetic is not. The news from the Spanish embassy are not about the lectures, and this is it. Okay. So let me get something to drink, and then we'll come back to this lecture in a moment.
Okay, so let's have a break till 10:10, and we'll resume then. Is that all right for everyone?
Fine.
Okay.
So hello, welcome back after the break. In the meantime, I have managed to pull the chat window on my second screen. So now I should be able to answer to questions in the chat during the talk, but also do not hesitate just to unmute and shout and interrupt me if something is unclear or plain wrong. So we stopped at the seismic waves 2 slide, where I introduced the Newton's equations of motion, and now we can move further with this. So we want to express the stress tensor as a function of the displacement. So in order to do that, we introduce the strain, which is essentially the divergence of the displacement, this EIJ tensor, and this stress tensor in an isotropic medium can be expressed. Yes? Any question? No. The stress tensor can be expressed as a function of the strain tensor in the following way, that we introduce two coefficients called the Lamé coefficients, lambda and mu, and lambda is just the diagonal part of the stress tensor, and mu is the off diagonal part, and EIJ is well, mu is showing the proportionality of the stress tensor to the strain tensor, but the non-diagonal part. So if we insert the first equation into the second equation, we can get this TIJ, this equation for for the stress tensor in terms of the displacement. Oh, now if we have this formula for the, so now we have what we want. We have the stress tensor as a function of the displacement. So we can insert this equation into the equation of motion, and that is going to be some heavy calculation, which is shown in this slide. And essentially, I don't want to follow this at this moment, but concentrate on the formula I have in the bottom row. So we have the second derivative of the displacement. Then we have two terms that are proportional to the derivatives of the lambda and mu, which are this proportionality coefficients. So if the material is not homogeneous, then we have these two terms. In homogeneous materials, isotropic materials, we don't have anything like that. And then we have the two terms that are proportional to the derivatives of the displacement. So we can do a little bit of algebra with this equation to arrive at the sort of the seismic wave equation. So first of all, we get rid of the first two terms by assuming that the nabla lambda and nabla mu, the gradient of lambda and the gradient of mu is 0. And then we have these two terms, and these two terms can be rearranged using this known formula in the top, which you, I think, remember from your electrodynamic lectures. And we obtain this equation, which describes seismic waves for an isotropic medium. And in order to solve this, one can do the following trick. The first trick is to take the divergence of both sides, which will give you one type of waves. So take divergence of the seismic equation, and then you arrive at an equation which looks like this, that the second derivative with respect of time to nabla times mu is some coefficient times the second derivative Laplacian with respect to the same quantity. And this already looks like a wave equation for this quantity, nabla times mu. And the coefficient lambda plus 2 mu over rho is the velocity of the wave. And this is the first type of seismic wave that I have already talked about a little bit some time ago. This is the P wave, which is the primary wave, pressure wave, and its velocity. So I will show you this P wave, how that works in a body in a moment. Then, so is that, you know, I know that it's very difficult to follow such a you know, avalanche of equations that are sent out to you, but let me know if something is completely unclear. If you want to follow this, I'll give you references at the end of these lectures, and you will have these lectures, and you can you know, rederive it. It's not very difficult to derive it, but I know that this may be a problem in following such a lecture. So I don't see any shouts in the chat window, so I assume it's okay. So let me go to seismic waves solution number 2. We take the curl of the seismic equation, and then we have this curl of a curl of a curl, and knowing what a curl of a curl is, and knowing the basic properties of that the curl of a vector, the divergence of a curl of a vector is 0, we obtain another wave equation, and this time for the curl of u, with a different velocity. So this velocity beta is square root of mu over rho. And this solution of the seismic wave equation is called the S wave. So we have two types of waves, the P wave and the S wave. These are called the body waves. And the body wave stands for the fact that these waves propagate inside a medium where we are far away from all the boundaries or surfaces. So these are inside the body. The P wave is called the primary wave because it has a higher velocity, so it arrives first. The S wave is the secondary wave, it arrives second. But also the P and S can stand for pressure wave or the shear waves, as you will see in a moment when I show you how these solutions look like. So the P wave is shown in this animation, and it is a pressure wave that moves into, so the particle motion is parallel to the direction of the propagation, and it is connected with density gradients, so that compresses the material, and then the material relaxes, but this pressure wave is transferred in the medium. The second type of wave, so the P can also stand for pressure wave. Yeah. Then the S wave is a different type of wave. Here the particle motion is perpendicular to the direction of propagation, and there is a shear force between the volume elements that is responsible for propagation of this wave. There is no density variation related to the S wave propagation, and as you saw a few slides before, the velocity of this wave is smaller than the velocity of the P wave. So the S can stand for secondary wave or shear wave or whatever you want to use. Now, these were the body waves. So these were the waves inside, far away from any boundaries. But very often we have to deal with waves that are happening close to a boundary. So we have to think, what would the surface waves be? And the surface waves, in order to find the surface waves, we need to solve the equation, the seismic equation, with specific boundary conditions. So the typical boundary condition is that we have a half space with uniform density in the lower half. Then the top half has zero density, which is, and that corresponds to a surface. And displacement has to vanish at minus infinity, and it has to vanish at plus infinity, but there is no displacement in the part where there is zero density. However, the displacement can move by smaller amount the surface, and so displacement can change the shape of the surface or the boundary between the uniform density, non-zero density, and the zero density part. This solution can be thought of as the linear combination of the S and P waves that are reflected of the boundary of the surface. It's a so you can try to solve these equations with such boundary conditions, and you can see the solutions in the books or texts that I will provide you at the end of the lecture. And I don't think that I want to bore you with long equations for much longer, but I'll just show you the two types of the surface waves that one obtains when solving these equations. One is the love wave, and this is the wave where the displacement is perpendicular to the direction of motion. So this is a linear combination, as you can suspect, of S waves. And there is no density perturbation or related with such a wave, and the surface layer is not moved in this way because the particle motion is parallel to the surface. So this is one type of wave, and the second type of wave is the Rayleigh wave, where the direction of propagation of where the particle motion is in ellipsis in the plane that is perpendicular to the surface and parallel to the direction of the propagation. The particle motion is counterclockwise when you when you look at the direction of propagation. And there are density perturbations related to such a wave, as well as the surface deformation that is related to such a wave. So these waves are kind of well known by people who have ever lived through earthquakes. They are the most causing the most disruptions, and they are the most dangerous for structures on the ground. So when you look at the what does it mean for the seismicity on Earth, we have the map of earthquakes around the Earth, and you probably have seen this map many times. This shows the faults and the regions where we have most earthquakes and volcanic regions. And this is not uniform of the Earth. That's in places where there is seismic activity, and the seismic activity is related to the heat flow and the plate tectonics. So the seismic activity on the Earth, there are some regions with more, some regions with less seismic activity on the Earth. A typical earthquake looks as follows. We have something that happens deep down in the Earth, in the crust. Some plates suddenly move, slip, and typically we have the first arrival is the P wave. Then it's followed by the S wave. And when these waves arrive, they cause, and their amplitude is relatively small. But then when they arrive at the surface, they generate the surface waves, and so the love waves and the Rayleigh waves that propagate and dissipate on the surface. If you have a wave that goes somewhere, reaches the surface, its energy has to be released somewhere. So some part of its of the wave is reflected of the surface, but some part is dissipated, and that's the problem because that causes the surface waves that propagate on the surface of the Earth, and these are love waves and Rayleigh waves, and the Rayleigh waves are the most causing the most destruction because their amplitudes are high. And also the Rayleigh waves are the waves where most of the energy dissipation is going on. So these are the earthquakes, which are the events with very high amplitude. But essentially, the earthquakes are not very important for gravitational wave detectors because you are not going to be taking data during a big earthquake. You are going to the only reason why we worry about big earthquakes is we want the structures not to be destroyed by these earthquakes. We are not going to be taking data during the earthquakes because the interferometers will be out of lock during that time anyway. So there is not much to worry about that. The bigger problem is the seismic noise, and the seismic noise are seismic waves of low amplitude that propagate all the time, and they originate in things we cannot control. So wind, sea waves, low scale seismicity, so rocks moving with respect to one another, really low amplitude earthquakes that go on all the time. And also, last but not least, the human activity. You have cars and trucks, you have people moving in, there is industrial activities, trains, and they all cause trembling of the earth. And this is something that we have to live with. So what is the typical spectrum of the seismic noise, and what can we do about that? So this is one of the seismic noise measurements in the Netherlands. The gray lines denote the seismic noise low value, seismic noise high value, and that's a general seismic model that is used for estimating seismic noise on the Earth. This is as a function of period, so that's the inverse of frequency. And these types of graphs where the density of points over a long period of time is shown is something that we use frequently in seismic physics. This line that is flat line at the low end probably corresponds to the times when the instruments were turned off, and that represents the self noise of the instrument. So that's not physical, but typically, there is some structure here. So and the peak here between 1 and 10 seconds, so between 0.1 and 1 hertz, corresponds to the sea wave activity. So this is related to the fact that the ocean waves pound on the ground, on the shores, and these ocean waves cause seismic waves, and the typical frequencies of these pounding is in the range of about 0.1 several to 0.5 hertz. Now a note on the units. You may be a little bit surprised with the units we have here. We have meters squared per second to the fourth per hertz, and that's log 10 expressed in decibels, which for many people, well, people working in electronics are used to that. People working in physics are At least I was not used to these types of units. So with the units, what we have, we first have to look at graphs like that, whether they show displacement, velocity, or acceleration. So this seismic noise shows a little bit of something that resembles square of the acceleration, except for the square root of hertz. So we have, first of all, we can show the time series of the displacement, velocity, or the acceleration, but we can also show the power spectral density, which is obtained by taking a Fourier transform, squaring it, and dividing it by the length of the time that we measured, and then we obtain a quantity like power spectral densities, which for displacement would be in the units of meter squared per hertz. For velocity, it would be meters per second squared, so meter squared per second squared per hertz, and the units for the power spectral density of acceleration you have just seen a moment ago. Then if we take a square root of it, we get the amplitude spectral density, and that's something that is also shown in this type of graphs, like some unit, some quantity per square root of hertz. Then the next point is that some in seismology, they like to use decibels, and so they like to show it on the log scale, and like here they multiplied by 10. So that's you know, another complication. But that's that's the way these things are presented. Okay, so we now have seismic noise, and we want to worry and think, how does the seismic noise affect the gravitational wave interferometer? So there are two couplings that we have to worry about. One is the mechanical coupling, and another is the gravitational coupling. So with the mechanical coupling, this thing is relatively easy. You know, the ground is shaking. It is the interferometer is connected, is built on the ground, so the shaking of the ground is transferred to the interferometer, and then the shaking of the ground is transferred to the interferometer. So this type of coupling can be mitigated by building attenuators, which from the basic physical point of view means hanging all of the elements that require to be stabilized on pendula, one after another, and the pendula have the property that if you look at the equation of motion of a pendulum, it transfers the vibrations that are below its resonant frequency, but it dumps the vibrations above the resonant frequency as the square of the ratio of the frequencies. So if you want to dump the mechanical vibrations, you just use a mechanical system to mechanically dump these vibrations. Then there is the gravitational coupling, and the gravitational coupling is shown here. If we have, you know, this is the set of pendula on which a test mass is being hung. But if we have a Rayleigh wave moving underneath the mirror, this Rayleigh wave is a wave of density and change of the surface, and that means that the gravity direction at the location of the pendulum is going to be affected, is going to be changed, and there is going to be a little of change of gravity, which will affect the motion of the screen, of the mirror. And that and such an effect cannot be screened. We don't have gravity screens. We have to measure it, and we have to subtract it in post-processing of the data. So here I'll have a few simple slides with the derivation of the gravity perturbation from seismic waves. I'll try to make them as simple as possible. So if we have some displacement perturbation U as a function of R and T, then the density perturbation is going to be minus divergence of the product of density and the displacement. So this is the basic thing we work on. And then the gravitational potential fluctuation is going to be minus G times the, there's the definition of the gravitational potential. We have to integrate the density perturbation with the volume and divided by R minus R naught. And a keen eye here will note that at this moment I am assuming that that this potential that the information about this potential fluctuation is propagating immediately. I don't use any retarded formula on the right hand side, but this is fine. Then we have to use a little algebra to transform the equation for the gravity perturbation. So we first insert the formula for the perturbation of the density into this formula, and then if we do integration by parts, you see a derivative in the numerator and the multiplied by a function. So you can integrate it by parts and see that one integral can be changed from the volume to a surface integral using Gauss theorem. So you are only getting the other part of this integration by part. So in effect, you are getting the following formula, and here I made a mistake. So there should be a nabla in the bottom formula. I'll correct it in a second. So that's the formula for the potential fluctuations. And then if we do, and here there is no error. Now the acceleration is the gradient of the potential. So you can see the potential fluctuation as the gradient of the top of the potential fluctuation. This should be a capital G. I will correct this, and that's the formula. What is really interesting to us is the case of a surface wave. So we have the density, which is some uniform density times the Heaviside function of a function of the distance, which means that we have some surface. So if we insert this formula into the potential fluctuations, we have to do the derivative of the product of these two functions, and that leads to two derivatives, and that can be shown that it works as so there are bulk, there is a bulk part to the potential fluctuation, and there is a surface part. which corresponds to the fact that we have potential fluctuations due to the fact that there are variations of the density in the material. And then there are some potential fluctuations due to the change of the shape of the surface, which corresponds to the fact that the distance between our test mass and the distribution of mass on the surface is being changed. So now the question is, which waves contribute to gravity fluctuations? So we have seen that there are two types of surface waves. There are the love waves and the Rayleigh waves. And the love waves do not change the surface shape, and also they do not lead to density fluctuations, so they do not contribute. So the main part that contributes are the fluctuations due to Rayleigh waves. So the Rayleigh waves are the only waves that cause the vertical displacement. So in order to characterize the relevant seismic field, we can constrain ourselves to measure just the vertical fluctuations and not worry about the horizontal fluctuations of the surface. So let me now show you what I think the problem is. I will stop share of this screen. I will now share a video to, okay, and if you see this looks more or less like what we want to characterize. Yes, we have a surface of the water, and let me put it again. We have some waves, different waves propagating in various directions, and you see the seismometers, which are these birds that are on the surface, and with the seismometers we are measuring the velocities in the top down direction, and we want to characterize the gravitational field by characterizing the seismic field by making a set of measurements like that. So it's a tough tough problem, but we can try to solve it. And here is an example of how that has been done. These are the histograms of seismic spectra at Virgo, and then the model of the Rayleigh wave Newtonian noise. So we see that the noise is of course at a much much lower level. The black curve corresponds to expected model sensitivity of advanced Virgo. So the expected noise is still below the sensitivity curve of advanced Virgo, but if we want to, if we push down the sensitivity of advanced Virgo, the Newtonian noise will be relevant in this case. And another example here is a measurement done at LIGO. The left-hand side panel shows a much wider range of frequencies than in the previous slide, and then there is a model of the Newtonian noise and the model of advanced LIGO sensitivity. So here you see that the Newtonian noise touches on the sensitivity of advanced LIGO, and therefore mitigating this noise and subtracting this noise is an important subject. So the gravity gradient mitigation strategy is essentially measure and subtract and use network of sensors find the best combinations. We don't know what the underlying field is, so we need to find what is the best combination for each particular location, and so we are here sort of in the dark. Then, in order to extract the best estimate of the gravitational wave, gradient noise, we use the Wiener filter techniques, and I think that there might have been lectures on Wiener filtering. And the best subtraction we can obtain is by a factor of a factor up to 5 of the noise related to the Newtonian noise. And a factor of a few is already quite a lot, because that means that, for example, for binary black holes, we can extend the range by a factor of a few. So if you can extend the range from, say, a gigaparsecs to 5 gigaparsecs, that's a lot. And that, in this respect, this is a very important astrophysics issue from the astrophysical point of view. Another thing is that if we decrease the sensitivity, if we increase the sensitivity and decrease the noise at low frequencies, we should be able to see binary neutron stars much earlier, and we should be able to localize them in the sky before the merger and set alerts. Look here, there will be a gamma ray burst, there will be a kilonova, there will be a merger in this part of the sky, and you can ask the electromagnetic observers to monitor a sky for a coming event. So in this respect, there is a connection between geophysics and astrophysics and gravitational wave physics. And it's an extremely, I think, exciting field to work on. So to finish, I have some further reading for you. There are one article in the Living Reviews of Relativity by Jan Arms. There is several books on seismology and geophysics. One of them that I used is the one by Peter Scherer, Introduction to Seismology. So I think I'll stop here and ask for questions.
Okay, I'm looking at the chat. There do not seem to be any questions on this second hour.
Well, I have a question, if possible.
Yes.
About the magnitude of the gravity gradients. So do you have an estimation of the level that it starts to affect our sensitivity? How many?
Okay, let me just come back to the slides. I'll start sharing again. Share this. So this is a slide with estimated value. So first of all, the gravity gradients are important for the Newtonian noise in the low frequency range. And you can understand it as follows. If you have a high frequency seismic wave, the wavelength of the seismic wave is such that underneath the test mass, we have a few waves passing by at the same time. So the contributions from several troughs of this wave cancel out. So for high frequencies, we don't care. For low frequencies, the wavelength is comparable or higher than, say, the typical distance between the test mass and the floor. And then the amplitude of this Newtonian noise, gravity gradient noise, is more important. So here you see that For example, for Virgo at 10 Hertz, typically we expect that the amplitude of the Newtonian noise in the gravitational wave detectors is about 10 to minus 22. In LIGO at 10 Hertz is about 10 to minus 22 as well. And this falls off very quickly. This should be falling off as frequency to minus fourth power. So at higher frequencies, it's not important. If you go to lower frequencies, that becomes a problem. And if you were asking what is the value of the acceleration in meters per second square, I don't have this number on top of my head. I would have to dig it out.
Is this, if you compare the two pictures, so left and right?
Yes.
Between, let's say, 6 and 8 Hertz, looks exactly the same. So if that...
Well, the shape should be the same, yeah, but the coupling is very weak. And also because of this effect that higher frequencies do not contribute less and less, the slope is different. But the wiggles in the left part graph and the right part graph correspond to one another. Is that clear or not? So
to understand, check if I understand it. So you now, so the wiggles in the left plot.
The wiggles in the left plot, which is the seismic noise spectrum.
Yeah, they are causing the sensitivity limitations in the right plot.
Yes, because they are causing, this seismic noise. This is the spectrum of the seismic waves that propagate underneath the test masses. So this noise causes gravity perturbations in the that affect the position and the motion of the test masses. So this translates into the Newtonian noise, the contribution to the noise, which is called the Newtonian noise in the right-hand plot. And this is a simple transformation. In the first approximation, this is a constant times, I think, the f to minus 3, frequency to minus 3. So when the left plot, the typical spectrum in the left plot is f to minus 1. So the spectrum in the right plot is about f to minus 4.
Thank you.
Okay, any more questions?
There seems to be a question on the
No,
chat.
no, it was just a comment. Yeah, the two different plots are basically the right one, if I'm correct, is the strain, while the other was the velocity, as
Yes.
Tomasz said.
Mm-hmm.
Okay. Okay. Thank you so much, Tomek, for this 2-hour session.
You're welcome.
We wished that this was under better circumstances, but unfortunately we couldn't.
Yeah, I mean, let's hope to meet in person pretty soon, and let's hope that this whole thing passes through and we are all safe.
Yeah. Thank you so much. Goodbye then. We're gonna carry on
bye-bye,
the
and have a good travel.
Yeah,
Safe
thank
travels.
you. Bye-bye.
Bye-bye.